It weighs less than a pound and is just slightly bigger than a clenched fist. Every day it beats over 100,000 times, pumping over 2,000 gallons of blood without stopping for anywhere up to 100 years or more. It is the human heart. The heart is located in the center of the chest, inclined slightly towards the left-hand side. It shares the interior of the rib cage with the lungs. In cross-section, we can see that it's hollow and divided into 4 chambers. The heart is basically a sack of specialized muscle filled with blood, oxygen-rich blood and oxygen-poor blood. Connected to these chambers are the largest blood vessels in the body. From these branch out the lesser blood vessels, which, along with the blood, comprise the rest of the circulatory system. The heart powers the circulatory system. It is the pump, and pumping blood is its one and only job. The circulatory system distributes food and oxygen to, and takes wastes away from, each of the individual cells of the human body. The blood vessels reach these cells by branching out into capillaries, the smallest and most plentiful blood vessels. The blood carries the food and oxygen, which pass through the thin walls of the capillaries and directly into the living cells. At the same time, wastes from the cells pass back into the capillaries. Without a constant supply of fresh blood, the cells would quickly die. It's the heart's job to keep the blood in motion. How does the heart accomplish this vital task? By looking at the circulatory systems of other animals, we can better understand the structure and action of our own hearts. Even a large jellyfish, which has no heart, uses rhythmic muscular contraction to circulate food and oxygen. It has a primitive circulatory system, consisting of a network of cilia-lined tubes. As the jellyfish swims, its muscles squeeze and stretch the tubes, circulating food and oxygen within them. If muscles are attached directly to a tube and made to contract in a regular rhythm, fluid can be made to flow through it. This is the simplest form of heart. If we place valves in the tube, we increase its complexity. Insects like grasshoppers have this type of heart. Active larger animals like the shark have circulatory systems that are similar to our own. The shark's heart is a single muscular sac divided into chambers. The shark has a 2-chambered heart consisting of an atrium and a ventricle. An amphibian's heart, like this frog's, is more complex. It has a 3-chambered heart consisting of 2 atria and 1 ventricle. An adult frog breathes air, oxygenating its blood in lungs. The oxygen-rich blood from the lungs passes through the left atrium and enters the ventricle, where it mixes with oxygen-poor blood. This mixing of oxygen-rich and oxygen-poor blood is a bit of a problem. It would be more efficient if no mixing occurred. Reptiles, especially reptiles like alligators, have partially solved this problem. They have a wall of tissue that divides the ventricle into 2 parts. The wall is not complete, but it does serve to greatly reduce the amount of mixing. We mammals have fully solved this problem. We have a wall of tissue called the septum that completely divides the lower portion of our heart into 2 separate ventricles. This is called a 4-chambered heart. The upper 2 chambers, the right and left atria, are the filling chambers. They receive the blood into the heart and push it down into the right and left ventricles. The ventricles' walls are much more muscular than those of the atria because they provide a more powerful pumping action. The circulatory system presents a confusing array of twisting and overlapping blood vessels. For ease in understanding, let's display the 3 major components in this fashion: the body, the heart, and the lungs. Our heart is not just a single pump. It's two pumps, side by side, each with its own atrium and ventricle. This division also separates our circulatory system into two parts. One part, powered by the right side of the heart, carries blood through our lungs. The other part, powered by the left side of the heart, carries blood through the body. The right side of the heart pumps the blood at a relatively low pressure to circulate it through the lungs. But if the left side of the heart pushed at this same pressure, it would not be enough force to circulate the blood efficiently through our bodies. It would be difficult to walk or even stand because our muscles wouldn't receive enough oxygen and nutrients. We'd have to be more like a reptile and have a low-slung posture and a more sedentary lifestyle. Mammals require a much higher blood pressure than reptiles do. Our upright posture makes this even more important. It takes a lot of force to push blood up against gravity. Other mammals need even higher pressure. The giraffe's heart has to pump blood straight up for 6 feet to reach the level of its brain. To handle this greater workload, the walls of the left ventricle have much more muscle than those of the right ventricle. The blood pressure that the left ventricle can deliver is 5 times higher than the right. The pressure difference is so great that if the lungs were subjected to the same blood pressure that the body receives, they would be destroyed. These, then, are the two great advantages of the 4-chambered heart. 1. Oxygen-rich and oxygen-poor blood are kept separate. 2. Blood pressure in the body can be much greater than blood pressure in the lungs. Let's follow the pathway of the blood through our circulatory system, identifying the major blood vessels connected to the heart. Let's start in the right atrium. Here, the oxygen-poor blood is pushed into the right ventricle. It's then pumped out of the heart into a short, thick artery called the pulmonary trunk, which branches into the 2 pulmonary arteries. The right pulmonary artery carries blood to our right lung. The left pulmonary artery carries blood to our left lung. Inside the lungs, the arteries branch out, ultimately leading the blood through capillaries. Here the blood picks up its cargo of oxygen. The capillaries then join into veins. Finally, the oxygen-rich blood exits the lungs in the right and left pulmonary veins. There are 4 of them, 2 from each lung. These 4 pulmonary veins connect to the left atrium, which pushes the blood into the left ventricle. The left ventricle pumps the blood out into the aorta. From the aorta, the blood is channeled through smaller arteries which branch throughout the body, ultimately leading to the capillaries, where the blood loses its cargo of oxygen and picks up carbon dioxide and waste. While in the capillaries, the blood will also pick up and distribute food, hormones, and other substances. From the capillaries, the oxygen-poor blood travels through veins which lead it into the 2 largest veins in the body, the superior and inferior vena caves, which connect to the right atrium. Bringing us back to our starting position. The blood passes through the heart twice during each complete circuit, once through each side of the heart. Now let's put the lungs and heart back into the body and take a look at the vessels in their correct position. Notice how the aorta forms an arch over the heart. One feature that most pumps have in common is valves, which keep the liquid flowing in one direction. The heart is no exception. Each chamber is followed by a valve, which prevents the backflow of blood. The valves located between the atria and the ventricles are made up of thick flaps of connective tissue. These are called atrioventricular valves. The valve that separates the right atrium from the right ventricle has 3 flaps or cusps, and it's known as the tricuspid valve. The valve that separates the left atrium from the left ventricle has only 2 cusps, and it's called the bicuspid or mitral valve. The valves that prevent blood from returning to the ventricles are called semilunar valves. The pulmonary semilunar valve leads to the pulmonary trunk. The aortic semilunar valve leads to the aorta. Each of the semilunar valves has 3 cusps or flaps. These 4 valves, working in pairs on each side of the heart, open and close in a steady rhythm. In fact, what we hear as the rhythmic sound of the heartbeat is actually the sounds of these valves closing. At rest, the heart beats about 72 times a minute. During strenuous exercise, our muscles require more oxygen-rich blood, so our heart will speed up to about 180 beats per minute, and it will contract with more force, increasing the amount of blood pumped by as much as 10 times. The rate at which our heart pumps blood is controlled by our autonomic nervous system, which means we don't have to think about it. Asleep or awake, our autonomic nervous system is automatically monitoring and adjusting the pumping rate of our heart, matching the flow of blood to our body's needs. Emotional stress can speed up the heart rate by sending out a warning to the autonomic nervous system. The anxiety we might feel about the big race will speed up the heart's pumping long before the race begins. Fear and anger are other strong emotions that can trigger an increased heart rate, as will strong emotions of the romantic sort. This emotional connection is why the heart has become so closely associated with romance. The heart symbol is the symbol of love. On Valentine's Day, we give each other cardboard hearts. Valentine's cards as an expression of caring and affection. Our hearts are said to fly like birds with joy, to flutter, to yearn for a loved one. We lose our hearts to others.
What?
Also, our hearts are said to stop with sudden surprise, or to break, and grow heavy with grief. We have seen that emotional stress can slow down or speed up our hearts, and that it does so because of the monitoring of the autonomic nervous system. But this isn't what makes the heart beat. In fact, when disconnected, the heart will continue to beat along by itself, setting its own pace. It's the muscle of the heart, called cardiac muscle, that makes the heart beat, and it's different from any other muscle found in the body. We can see how the arrangement and structure of cardiac muscle cells differ from the other 2 types of muscle cells, smooth muscle and skeletal muscle. Both smooth and skeletal muscle cells will contract only when our nervous system commands them to. Only cardiac muscle cells can contract on their own. They have the ability to start and transmit their own electrical impulses to contract. Each individual cardiac muscle cell has this ability, but they don't all contract independently. They obey the dominant electrical impulse. When connected in a chain, the dominant impulse is passed along each cell. Together, the whole mass of cells contracts when the impulse passes through. Some cardiac muscle cells can generate and carry electricity better than others. They initiate and channel the dominant electrical impulse. They form a kind of electrical wiring pattern throughout the cardiac muscle. The largest concentration of these specialized cells is located in the right atrium. It's called the pacemaker. It acts like a spark plug to begin each heartbeat, stimulating the muscles in the atria to contract, and setting off a second concentration of cells which stimulates the ventricles to contract. The electrical impulses from your heart can be detected on your skin by sensitive electrodes. These tiny electrical impulses are transmitted to an electrocardiograph machine. This man is undergoing a complete heart checkup. The doctor is evaluating how well his heart beats at rest and during exercise. He's been having chest pains, and he's afraid that he may soon have a heart attack. In the United States, over 4,000 people suffer heart attacks every day. It's the leading cause of death in the U.S. For this man, it needn't have been this way. In high school, he was active and had a strong, healthy heart. But at this time, he developed some bad habits. He began smoking cigarettes and drinking alcohol. His diet consisted of foods rich in sugar and fat. He didn't keep up a regular exercise program and let his body become overweight. Now, 30 years after high school, this man's heart is showing signs of giving out. Whenever it speeds up, he gets pains in his chest and must sit down and rest for a few minutes. His pain is caused by premature hardening of the arteries, arterial sclerosis. This is most dangerous in the coronary arteries, which branch off from the base of the aorta. The heart muscle depends on the constant supply of blood supplied by the coronary arteries. Over the years, the inner walls of these arteries have become coated with an excessive buildup of material called plaque. Now this artery is so narrow that even a tiny blood clot could obstruct it. If a blood clot were to get lodged, say, here, it would block the flow of blood to a large portion of the heart. Without fresh blood, that portion would die. This is a heart attack. As a portion of the heart begins to starve for fresh blood, the person first feels a vice-like pressure and pain in the chest, which often spreads to the arms, especially the left arm. This time, his chest pain will not go away when he rests. It continues to get worse. In a severe heart attack, the difference between life and death is often prompt medical care. The best chance is in a hospital. Unless the blood clot can be cleared away within the first 4 to 6 hours, the starving heart muscle will die. Most people who have survived heart attacks have experienced the death of some portion of their hearts. This portion will never contract again. The dead muscle is replaced by scar tissue. Often the scar tissue will interrupt the electrical pathways, causing an abnormal heartbeat. In that case, an artificial pacemaker, complete with batteries and electrodes, can be implanted, giving a timed electrical boost to the ailing heart. Heart surgery has become one of the most exciting areas in modern medicine. This is primarily due to the heart-lung machine. For a few precious hours, this machine pumps the patient's blood, bypassing the heart, allowing the surgeon time to stop the heart and operate on it. Since its introduction in 1953, the heart-lung machine has made possible all kinds of surgical procedures. A defective heart valve? Well, now we can cut it out and sew in a new artificial heart valve. A bad case of clogged up coronary arteries? Well, now we can take a vein from the patient's leg and sew it from the aorta to a coronary artery, bypassing the clogged up section. In cases where the patient's heart is in hopeless condition, the entire heart can be removed and replaced with a healthy heart from a person who has just died. For those too old or too ill for a heart transplant, there is the artificial heart. This is the Jarvik 7 model. It was first implanted in a patient in 1982. It represents the first attempt at a permanent artificial heart. Unfortunately, heart replacement surgery is far from being a complete cure. Patients who receive these procedures must be under continuous medication and medical supervision. That's why it's so important to take care of the heart you were born with. There is still no replacement that works as well and lets us live our lives with as much promise. The foods we eat, the ways we deal with stress, and the amount of physical exercise we get all affect the health of our heart. Its well-being, and therefore ours, depends on the quality of our lives.